So now I'm going to change subjects here, but the subject that I'm going to talk about next is very, very closely linked. Namely, I talked about implicit differentiation. Now we're going to just talk about dealing with lots of variables and rates of change. So essentially, we're going to talk about the same type of thing. So I'm going to tell you about a subject which is called related rates, which is really just another excuse for getting used to setting up variables and equations. So here we go, related rates. And I'm going to illustrate this with one example today, one tomorrow. So here's my example for today. So again, this is going to be a police problem, but this is going to be a word problem, and sorry, don't want to scare you, no police. Well, there are police in the story, but they're not present. But I'm going to draw it immediately with a diagram because I'm going to save us the trouble. Although, the point here is to get from the words to the diagram. Okay, so you have the police, and they're 30 feet from the road. And here's the road. And you're coming along here in your, let's see, in your car, going in this direction here. And the police have radar, which is bouncing off of your car. And what they read off is that you're 50 feet away. All right? They also know that you're approaching along the line of the radar at a rate of 80 feet per second. Okay? Now, the question is, are you speeding? Right? That's the question. So when you're speeding, by the way, 95 feet per second is about 65 miles per hour. So that's the threshold here. So what I want to do now is show you how you set up a problem like this. All right? This distance is 50. This is 30. And because it's the distance to a straight line, you know that this is a right angle. So we know that this is a right triangle. And this is set up to be a right triangle, which is an easy one, a 3, 4, 5 right triangle, just so that we can do the computations easily. All right? So now the question is, how do we put the letters in to make this problem work, to figure out what the rate of change is? So now let me explain that right now, and we will actually do the computation next time. So the first thing is you have to understand what's changing and what's not. And we're going to use t for time in seconds. Okay? And now an important distance here is the distance to this foot of this perpendicular. So I'm going to name that x. All right? I'm going to give that letter x. Now, x is varying. The reason why I need a letter for it as opposed to this 40 is that it's going to have a rate of change with respect to t. And in fact, it's related to the question is whether dx dt is faster or slower than 95. Okay? So that's the thing that's varying. Now, there's something else that's varying. This distance here is also varying, so we need a letter for that. We do not need a letter for this, because it's never changing. We're assuming the police are parked. They're not ready to roar out and catch you just yet. And they're certainly not in motion when they've got their radar guns aimed at you. So you just sort of need to know something about the sociology and style of police when they're, okay? So you need to know things about the real world. Now the last bit is, what about this 80 here? So this is how fast you're approaching. Now that's measured along the radar gun. I claim that that's d by dt of this quantity here. So this d is also changing. That's why we needed a letter for it too. So next time, we'll just put that all together and compute dx by dt.